Welcome back to week 8 of the ma161 calculus. My name is Götz Pfeiffer and this video is about derivatives of products and quotients of functions. Bad news first. The derivative of a product of two functions is not the product of the derivatives. This can be seen in an example whose ingredients we know quite well by now. Let's have two functions f and g, both defined to be just x. Then, since the derivative of the x function is the constant 1, both f prime and g prime are 1, and so also the product f prime of x times g prime of x is 1. And this is the product of the two derivatives, and it's 1. On the other hand, the product of the two functions, both being x, is x times x, that's x squared. And we've just seen that the derivative of x squared is 2x. So the derivative of the product of the two functions is 2x, which is different from the 1 that is the product of the two derivatives. So why is this? Let's try and visualize this in graphical terms. Suppose we have two quantities u and v, which both depend on another quantity x, u being a function f of x and v being a function g of x. Then the product uv can be visualized as the size of a rectangle here, with side lengths u and v. Now if x, the quantity that both u and v depend on, changes by delta x, then u and v change correspondingly by amounts delta u and delta v. Delta u here being the extra width of the rectangle, and delta v here being the extra height in the rectangle. And this change of delta x in the x variable results in a larger rectangle, now with side lengths u plus delta u and v plus delta v. The change in rectangle size is measured by these three colored rectangles. The one of size u times delta v, the one of size v times delta u, and one of size delta u times delta v. So if we want to calculate the rate of change, we divide this equation here, which describes the absolute change, by delta x, and then we let the delta x go to 0, compute the limit of this expression to find the derivative in Leibniz notation as u times dv over dx plus v times du over dx plus 0 times dv over dx. Since this delta u goes to 0 when delta a goes to 0, u and v are both constants, and delta v, the limit of delta v over delta x, is the derivative dv over dx, and similarly for the delta u over delta x. That's the product rule. Here in Leibniz notation, d over dx, the derivative with respect to x of the product uv, is u times dv over dx, the derivative of v with respect to x, plus v times du over dx, the derivative of u with respect to x. Or in prime notation, if both f and g are differentiable functions, then f times g prime is f times g prime plus g times f prime. The derivative of a product is a sum of two mixed terms, each being the product of one of the functions and the derivative of the other. Here's an example. Let's try and find the derivative of a function defined as x times e to the x. And then, if we can, the second derivative and so on. Maybe we can spot a pattern that describes the nth derivative of this function. So the derivative of a product, the product of x times e to the x, is the first factor, x, times the derivative of the second, the derivative of e to the x, plus the second function, e to the x, times the derivative of x. Now we know the derivative of e to the x is e to the x itself. The derivative of x is the constant 1. So we can compute this derivative of the function, which is a product of two things, as x times e to the x plus e to the x times 1, which is x plus 1 times e to the x. The second derivative of this same function is the derivative of the first derivative. So the derivative of the product of x plus 1 and e to the x. Applying the product rule again, this derivative is the first function, x plus 1, times the derivative of the second, e to the x, plus the second function, e to the x, times the derivative of the first function, x plus 1. The derivative of e to the x is e to the x itself. The derivative of x plus 1 is the constant 1. So we can compute this as x plus 1 times e to the x plus e to the x times 1, which is, taking e to the x out as a common factor, x plus 2 times e to the x. Is there a pattern emerging? Well, if you like, try another one. Try and find the third derivative as the derivative of the second derivative. You would go through a similar calculation using the product rule again and find that the third derivative is x plus 3 times e to the x. So in each step, for each derivative there's one more added to this x plus term here, meaning that in the nth step, the nth derivative of this function is x plus n times e to the x. Here are some more examples, applications of the product rule. Here's an example where we only have partial information about the second factor involved. Here's a function given as the product of square root of x and the function g of x, of which we only know that g of 4 is 2 and the derivative of g at 4 is 3. Let's try and find the derivative of f at 4. Applying the product rule to the product square root of x times g of x, we get that this derivative is the first factor, square root of x, times the derivative of the second, that's the g prime of x, plus the second factor, g of x, times the derivative of the first factor, which is the square root function, and its derivative is 1 over 2 square roots of x. So we get this formula for the derivative of x from the product rule, and now we can try and substitute 4 for x in this expression to evaluate the derivative of f at 4, and we find it's the square root of 4 times the derivative of g at 4 plus g at 4 divided by 2 square roots of 4. And since we know g prime of 4 and g of 4, this gives 2 times 3 plus 2 over 4, which in total is 13 over 2. Now using the product rule in the presence of only partial information on one of the factors. And here's an example that illustrates the fact that sometimes the product rule can be overkill. Let's try and differentiate f of x defined as 2x cubed plus 1 times 3x minus 2. Looking at the expression, this is a product, so the derivative would be a case for the product rule, and we can try and apply it. First solution, f of x is a product of a u term and a v term, where u is 2x cubed plus 1 and v is 3x minus 2. The derivative of u is, and that's a polynomial, that's 6x squared. By using our rules for computing derivatives of polynomials, the derivative of the v term, v prime, is 3, and then we can compute, using the product rule, the derivative of u times v as u times v prime plus v times u prime, and bring it all together, and adding it up gives 24x cubed minus 12x squared plus 3. Or, wait a minute, we could expand this product, multiply everything in the left term with everything in the right term, to find that f of x really is a polynomial, 6x to the 4 minus 4x cubed plus 3x minus 2, and we can compute its derivative by rules 0 to 4 as 24x cubed minus 12x squared plus 3. 24x cubed being the derivative of 6x to the 4, 12x squared the derivative of 4x cubed, and the 3 here the derivative of 3x minus 2 as derivative 0. That might be quicker, under certain circumstances more straightforward. So just as a small warning, not everything that looks like a product is or should be treated as a product. Quotients are similar. Well, similar first of all in the sense that it's not true that the derivative of a quotient would be the quotient of the derivatives. We can motivate the actual rule for quotients in a similar way as we've done this for products. I'll skip this for the moment and move this to the end of the video, where you can skip it too if you feel like it. So I'll give you the rule. The quotient rule, if f and g are differentiable functions and g is not 0, then the derivative of the quotient f over g is g times f prime minus f times g prime divided by the square of g. The derivative of a quotient is the difference of mixed terms, similar to the ones in the product rule, divided by the square of the denominator. For example, if we try and differentiate e to the x divided by x, then the top function is e to the x, the bottom function is x. And the derivative of e to the x is just e to the x, the derivative of x is 1. So here the quotient rule gives f over g prime second factor times the derivative of the first factor minus first factor times the derivative of the second factor divided by the square of the denominator. In this case then is x times e to the x minus e to the x times 1 divided by x squared. G of x is the x function, and that, taking out e to the x as a common factor, gives x minus 1 over x squared times e to the x. Rational functions are quotients of polynomials, so the quotient rule now enables us to differentiate rational functions. Here's an example of a rational function. F of x defined as x squared plus x minus 2 divided by x cubed plus 6. And here on the right I have the graph of this function in dark blue. It has a vertical asymptote somewhere here, near 2 but not exactly at 2. I guess there where x cubed becomes -6, and then this expression is not defined. And apart from that, it lives close to the x-axis here. And then in light blue we also see the graph of the derivative of this function, which records the slope of the dark blue graph at the various points over the x-axis. And you see that where the f function rises quickly, the derivative is big, and where the f function is not rising at all or only rises a bit, where the slope is close to 0, the light blue function is close to 0. Sometimes it's interesting to compare the graphs of the original function and its derivative. But as far as the calculation is concerned, here this works as follows. By the quotient rule, where the derivative is the bottom function, x cubed plus 6, times the derivative of the top, minus the top function, x squared plus x minus 2, times the derivative of the bottom, x cubed plus 6, divided by the square of the bottom function, x cubed plus 6. The derivative of x squared plus x minus 2 we can calculate as the derivative of a polynomial. That's the derivative of x squared plus the derivative of x gives 2x plus 1. The derivative of x cubed plus 6 is the derivative of x cubed, which is 3x squared. And if then we fill this all in, we multiply these out to expand these two products of polynomials, and then we calculate the difference between the two and find that the derivative of this function is minus x to the 4 minus x cubed plus 6x squared plus 12x plus 6 divided by the square of x cubed plus 6. Now that's a typical application of the quotient rule to the derivative of a rational function. That's it about the product rule and the quotient rule. If you want to hang on, I'll quickly go through the motivation for the quotient rule. In a similar way as we set up the reasons for why the product rule is like the product rule is, using the same setup, having a quantity u as a function f of x and a quantity v as a function g of x, we let x change by delta x, and then u and v change by delta u and delta v respectively, and then we can calculate the change in the quotient u over v as the value, the quotient of the bigger values, u plus delta u divided by v plus delta v, minus the original quotient, u over v, which, when we bring this on a common denominator, v times v plus delta v, gives this expression that simplifies to v times delta u minus u times delta v divided by v times v plus delta v. And as we did it in the product rule, this describes the change in the quotient. In order to determine the rate of change in the quotient, we divide this whole thing by delta x and then calculate the limit as delta x approaches 0 to get the derivative of the quotient. And the derivative, the u over the x of the quotient u over v, is the limit as delta x goes to 0 of the expression we calculated just here, the change in the quotient divided by delta x. And then a careful application of the limit laws, where the limit of a quotient is the quotient of the limits, the limit of a difference is the difference of the limits, and so on, taking out constants here, we find that this limit is the limit as delta x goes to 0 of this expression involving delta u over delta x and delta v over delta x, which in the limit are the derivatives of u and v with respect to x, just the same as they were in the case of the product rule. And delta v goes to 0 when delta x goes to 0, so the denominator here approaches v squared, and we end up with this expression, which in Leibniz notation is the quotient rule. V times the derivative of u minus u times the derivative of v divided by the square of v. And here and the result of the application of the limit laws is illustrated, and the limit of this quotient becomes a quotient of expressions which involve the limit of delta x going to 0 in various places. That's the application of the limit laws, which is a nice exercise if you want to go through this by hand. And the fact that delta v approaches 0 as delta x goes to 0 follows from the fact that the v as a function of x, g of x, is differentiable, and that's the assumption we make here. And earlier we found that differential implies continuous. So this function is continuous, and that makes delta v go to 0 and delta x goes to 0. That's it for the product rule and the quotient rule. That's really the end. And next time we look at derivatives of trigonometric functions, the sine, the cosine, and the tan function.